What is the question, guys, here? What is the time complexity, big O, to add an element into an array that is full? Not that I'm using extendable array. So who said O of 1? There's 20% that got wrong. So who want to just explain why they thought it's O of 1? Yes.
I assumed it was a linked list implementation of an extendable array.
It shouldn't be. Why? Because we're saying you want to add an element into an array. So we're adding an element into an array, okay? And we're saying, okay, we're using extendable arrays. In this case, what did we explain last time, guys? You remember the normal push and the special push? Mm-hmm. What did we prove? That whenever we want to add something and it's full, the array we're going to copy. So we're going to create a new array that may be double the size, and we're going to copy what's in array A into array B, and then add it. And we actually took our time to prove that it's going to end up with all n. Okay, so if you got this wrong, review the slides again that we talked about it in the last session. Good. So now let's start covering our very interesting ADT. So why this ADT is important? So what did we cover so far? So far, we talked about stacks, queues, right? And then we talked about sequence, lists. What is the common thing between everything so far? They are what when it comes to the time? Linear. Did we get anything less than O of n? Okay, so far, everything was linear. Now, someone, maybe a future you, said, you know what, challenge accepted. I'm going to find a way that we can find something that is better than linear. I want to find a way to access elements in a data structure where it will only take O of log n, not O of n. Okay, so that's what we're trying to cover. So from now on, you're going to see a type of an ADT that we will use later on to implement different kind of maybe queues, for example, but where we're going to be able to access things faster. So this is going to be based on trees. So we're going to cover now general trees, going to focus more specifically in this course about binary tree. Then later on, we're going to talk about binary search tree, AVL tree, and other things. But let's start with the trees. So what are trees? Who remembers graphs from discrete structure? Exactly. So the idea of graph here, this is a graph. The tree is very similar to a graph. We just don't have a full cycle. So we don't have a cycle like this, right? There is a cycle here. Okay. If we look here, guys, always remember there will be a root, parent-child relationship. Okay, so these will be roots, and then these here will be what? Leaves, because we're talking about a tree here. And then the ones inside them, we're going to call them internal nodes. So these here are going to be called external nodes or leaves. So let's take a look here, guys. That's the basic stuff that we're going to cover. So it's stick in our head. So roots, internal nodes are what? B, F, C, for example. And then we have external nodes, we named them. Also, we'll have ancestors and descendant. All of this are very easy for you to follow. Now, what I want you to focus on, very important us whenever we want to try to figure out the distance of something, we're going to work on the height. Height is something very important. If I ask you, what is the height of this tree? It's going to be 3. Why? The way that you want to calculate it, you start from the root till the longest leaf. So that's the longest part. you're going to count these. So that's 1, 2, 3. You don't count the nodes. Okay, guys? So that's how we do the height. Always remember this. Now, the depth is not the height of the tree. The depth, if I asked you, what is the depth? For example, what is the distance between B and I? So it's not about the whole tree. It's going to be about specific nodes that I'm going to tell you about. So what is the depth of from B to I? You're going to say 2. Second. Okay, so you got the general idea here of the tree. Now, here, is this a data structure for us, or is it still an abstract idea? Did we build this? Did we implement it? Okay, so what is it? Abstract. Can we call this abstract data type now? What's missing for it to be called abstract data type? Yes? So let's say we said we want to put specific data in it. What else will make it, will define?
The data, so some functions.
Operations, exactly. So functions or operations or methods. And then we said also, of course, the error. So we need 3 things. So for me to transform the idea of a tree into an ADT, I need to specify what kind of operations I need. So of course, we always need the size is empty and then elements. Now element, let's put it on the side for now. We'll talk about it. And then we want position. So I want, let's say, to know the position of this node C. So I want to be able to get the position. For now, still, I know it's not very clear to you because we don't know if we're going to use array or linked list or whatever. Now just think about the abstract idea here. And then we want to be able maybe to what? Swap elements. So I want to swap C by G, for example, let's say. So all of these are what? Are methods. Replace element. Now, I want to be able to check if a specific node is the root or not. Also, I want to be able to know, is it an internal node or external node? So all of these operations make what? This as a ADT. Now, what is the problem with this method? This method, we're going to call it like a major. It's costly because I'm actually telling you have to get me all the elements. So you'll have to traverse through the whole tree. So this is going to be costly for us, for example. We're not looking for a specific node. We're not looking to know if this node is internal or external. No, we want all the elements. So this is called like a major operation where it's very costly for us. Now, where do we use this ADT? We use it in applications like this. So technically, we want to make a tree. The reason here is it will save me time to go and get something, right? So that means the main idea here that I'm designing, I'm putting my data in a way that when I want to traverse inside this data structure, it will be faster for me. Because let's say I have a normal array like this, which is what? I want to access something, it's O of 1, correct? But if I want to add or delete, it's going to be O of n. So anyway, it's linear. Now, what if I want to organize my data in a way that, let's say I want to go here. So look, if I go here, it's going to be like this, like this. I didn't even look at these things. So it's faster. So that's the idea of the data structure or the data type of a tree that will be able to access something in a faster way. Now, that means we're going to talk about traversal. So how can I traverse this tree? Because it's not going to be linear. I'm not going to go step by step. So one of the ways to traverse is called pre-order. When is pre-order used? What do we mean by pre-order? We're going to visit the node that we are in before moving further. If you look about on chapters, right? Like if you're looking on a document, you're going to read this title, you're going to chapter 1, right? And then after that, you're going to go to the sections inside this chapter. So if I want to traverse this, it's going to be this first, second, third, fourth, and then now I'm going to the here. So in this kind of application, we're going to use the pre-order. We're going to talk about it more. There's a pre-order. Another way is going to be called post-order. So when I'm going to be using the post-order traversal, think about if I want to calculate the memory or the size in a folder. What do we do? So I arrive to this folder. Do I calculate the size of this? So usually the way it's done is I go here, I go to this one. So this one is, let's say, 3 kilobytes, then this one, then I go back. Okay, so that's called post order. That means I'm not visiting first, I'm reaching here, and then I'm going backward. So 1, 2, 3, then 4, 5, 6. Okay. Now, we don't want, yes, James.
Thank you. My question is, how are we able to put the pointers for all three?
Hey, so that's what we're going to explain in detail, but now I'm just giving you a general idea so you don't get lost when we go into the technical details. Because if I jumped right away on implementing this, you're going to be lost why we're even implementing it, why we're doing this, why we're doing that. So I'm just giving you an idea that why this is very important for us from a programming perspective. It's going to save us lots of time. So imagine you're going to be able to access something to search. Let's say you want to search in a database. Linear is what? It's going to take me 1 million seconds. Log n, we calculated last time, is going to be much, much less than that. Okay, so that's why it's important to organize your data in a way where it's easier for you, for example, to access it. Now, what we care about in this course specifically is the binary tree. But also, we're going to cover the general tree when we do 2-4 trees. But for now, binary tree is a bit more concise for us, so we're going to be able to design it in a better way. So who's going to help me to fix this, or not to fix, to create a new ADT for a binary tree? I gave you the operations for an ADT, it's general. So what would be different if I want to do this here? What would be the difference? Because can I use the other ADT for this? The other ADT is general tree. It's not specific, it's not binary. So let's start step by step. What is the binary tree, Taha?
Each node has only two.
Only two. So that's the first step. Only two. That means it's going to always have what? Left child and right child. So if I want to add an operation, do you remember in the normal tree, for example, I checked, is this internal? Is this external node? So in this ADT, what would I put some operations to define this ADT? Yes.
Get left, get right.
Yeah. Is this a left child or is this a right child? Or also, as you said, yes, Ryan.
Internal, you would check if there were no children at all. When I check if it was internal, if it had any children, then it would be internal. So you is external, you check for
Also, so is external, is internal, is similar to the other ADT, so we can use the same logic. But for example, here, we cannot use is left or is right to the other one because it's not binary. But this one, we're going to add, for example, these two operations. So now we're just understanding how we're actually defining an ADT. So we need to define specific operations to form this ADT. Also, so children are ordered. That's very important. So there's left and there is right. The other thing is that each node has at most 2 children. That doesn't mean they cannot have 1 children or be a leaf. At most 2 children. So it can be 0, 1, or 2. Now, these are very important for you to pay attention to it because there is a bit of different definitions online for these things. Because you may read the word full online. That means perfect in our case. And full is this. So please, in the exams, midterms, and everything, you're going to follow the definitions from the book that we're studying of. So don't get confused. Okay. So what is the difference between this and that? We're going to call a tree as full binary tree when each node, it's either a leaf or it has 2 children. In this case here, this node has only one child. So we cannot call it full. Now, that's what I want from you to analyze here. I don't want to go right away to implement this. Why are we even considering defining something as full and giving all of these specifics? Why do you think we're doing this? Let's think together. As we said we want to try to do some critical thinking to improve our soft skills. So why do you think someone sat here and said, you know what, I defined a binary tree, I want to also define a full binary tree? Why? You had a...
Which say that, so that we don't go programming and then we go back to conception and go back and forth.
True, but why did we choose this thing? Why didn't we just say, okay, I can have this? Why I'm deciding that, for example, it needs to have two? Yes?
I assume because with a non-full option, if you kept going down, you'd augment the height, when you can still fill out other roofs to shorten the height.
Beautiful answer. So guys, what is my aim here? My aim is to organize, because what is a data structure? Creating a data structure, that means you're organizing your data in a structure that is very efficient to access your data from, right? If I kept doing this, guys, for 1, 2, 3, 4, 5, 6, 7, 8. 8 nodes. What is the height here? Is 1, 2, 3, 4, 5, 6, 7. So the height is 6, correct? Because we're measuring these 1, 2, 3, 4, 5, 6. That's how we measure the height, is the thing. While I can do the same thing here, like this, for example. So how many are 1, 2, 3, 4, 5, 6, 7? And then I'll do this. So the height here is only 3. So we want to come up with a structure that I can easily explain for the machine, because you have to explain this into the machine. The machine will not look at this like you and say, okay, this has only one child. You have specific specifications to have a better thing. So that's very good. It's Joel, right? Your name is Joel? Thank you. Okay. Now, what is a perfect binary tree? So we said the full binary tree, it either has 2 children or leaf. A perfect binary tree when you have everything. Like, so this now is a perfect thing. So a perfect binary tree is perfect. It's fully condensed and everything. Again, online, they may call this as full. I don't listen to anything. Listen to it after you graduate from this course, because in the midterm, we're going to use these terminology. So this is very good for us when we have a perfect binary tree. That means we have the height is 3 and it is condensed. Good? Now, there's something called complete binary tree. This is going to be a very, very important concept for us. Why? Because we're going to use this to implement something called heaps. Why we have complete binary tree? Who can answer me philosophically, from a philosophy perspective? From a life philosophical perspective, why would we have this? Because life is not perfect. We will never have very, very, very rare that you're going to have a perfect tree. So we need to also come up with something that is almost perfect. True? Because imagine that always your data is going to be like this. It's not going to always happen. So we need to come up with something almost perfect. That means a complete binary tree, the definition of it is that this part here, what is h here? What is the height? Who can tell me? Raise your hand. Yes? You raised your hand or no? So next to you.
2.
2? Why 2? So sorry, the height of everything for the whole tree
It's 3 then.
is 3. So the definition of a complete binary tree that h minus 1 is perfect. Always h minus 1 is perfect. So the height minus 1 is perfect. Then the other criteria for a complete binary tree that it has to be what? Left filled. What do we mean by this? Now, if I want to put I want to add the next element to this tree, I can only add it here, then here. I can't add it here. It has to always be filled from the left to the right. You're going to ask me why? Because again, the one who came up with this idea, is that it's going to be much more efficient for us to organize and search. Because if you always know that you're inputting your data from the left to the right, you made it easier for you to do a search, because you're going to always know that, for example, you're starting from left to right. So two main things I want to know here is that a complete binary tree, which is the more practical thing for us, is going to be h-1 is perfect. Good, guys? Okay, what does this mean? That means if I want to have a full binary tree, okay. So now, can I say this is a full binary tree? Okay. Now, are you sure? Who says, you say no? Who says no? Raise your hand. Who says yes? Okay, why no?
I just think.
Joel, why no?
Assuming on the right side, the two nodes can be moved to the left side to make it more efficient.
These, it has to be moved to the left. Okay, another answer? Why no? Riley?
Yes.
Who said also no and has a different answer than yes?
As you said, it's only complete when you have the left branch.
Very good, but the question here, is this a full binary tree, not a complete binary tree? Yeah, we're asking about full. So you want to do another voting. So who says this is not full binary tree? Raise your hand. Okay, you want to answer why? Okay, very good. So that's why I'm asking you guys, because you're going to have lots of different things when it comes to this. Guys, so listen to me very carefully for this time. Full binary tree. A full binary tree is called full only if these are leaves or has two children. That's it. So this is a full binary tree. Always. Is this a complete binary tree? No, because it has to be what? Left filled. Is this the perfect binary tree? No, because it has to be all on the same level. So what do we have? Full, perfect, and then complete. Good. So now we actually got the idea. Yes. Sorry? So full and perfect will be the same. So not the same. So a perfect tree is also a full tree. And yes, debatably, you can say this is a complete binary tree when it is when it's perfect. So
Like 0 leaves.
exactly. Yeah. So technically, you can still call it complete if you want. Okay. But it is perfect. Okay. Very good. So just very quick, if someone is following up with us with the book, and the book, sometimes you're going to find what? Dummy leaves that are empty, they don't have any elements, and some other times there's no dummy leaves. So don't get confused. The only idea of a dummy leaf is that it doesn't contain any actual element inside it. It's just a way for us to check if this is a leaf or not. So in here, to explain things, sometimes you're going to see dummy leaves, sometimes no. Has no meaning other than these are empty. So very, very, very famous use for this ADT of a binary tree is a decision tree. Okay, decision tree, especially if you want to work with machine learning, you're going to always be using decision tree. So we all know the decision tree. You want a fast meal or not? If yes, that means all of this, I'm not going to look at it. I'm going to go here. How about a coffee? Yes, no. Okay. It's a decision tree. Now, let's give some examples of the use of these trees. How can we use, or when do we want to use a binary tree? And then we go to the implementation. Yes, James. Yes, of course. Sorry, just. Of course, guys, I'm going to publish the full notes after the section. Now we're going to give a few examples on when to use the binary trees. So this is one case. Another case, guys, in arithmetic. Let's say we want to calculate something. We have a formula that we want to calculate. So again, how is the machine reading this? Remember, we said we can use a stack to do it. You remember, like we can put the parentheses and do a stack and then get it popped and all of these things. We do two stacks, one for what? One for numbers, the other one is for operators. Okay, so a tree here can be used also for a binary, for an arithmetic. So this is one method. Let's take some examples. Okay, before we take the example, let's officially explain this. So what do we mean by n? When we say n, that means it's the number of nodes. Okay, the same thing when we used to say there is n elements in the array, we're saying the size of the array. When I say n, it's the number of nodes. Okay, the same idea. If you see e, we're referring to the external nodes. I, we're referring to the internal node, and h, the height. So as you can see here, guys, what is the height here? So the height is equal to 3. Also, the levels, we're going to always start from 0, so it will match the height. So the last level will be the height. Okay. Again, maybe online in a different book, it will be different, but that's how we use it in this book. Yes.
We count the dummy nodes when we're counting the height.
That's why sometimes if I give you dummy nodes, that you count them. If I don't give you dummy nodes, you don't count. Yeah. So what do we notice here, guys? What is the number? So in this first level, we have 1. And the second level, how many nodes I have? 2. 2 to the power of 2, 2 to the power of 3, right? So usually, the level L will have 2 to the power of L nodes. So this you need to. Now, I don't want you to memorize these things in the exam, in the midterm. Just draw a small tree like this. It will make sense for you. Draw it on thing and start counting it. It will work fine for you. So all of these are properties of a full binary tree. In the video that I'm going to publish, there is a detailed mathematical how are we proving these. I'm not going to spend much time on the mathematical thing. You can watch it if you're interested. For example, how do we know that E equal I plus 1 all the time? How we know this, how we know that? Yes?
Do we need to know the math of it, or can we just know that E equals I plus 1?
No, you don't need to know it. But again, always as a computer scientist, as a graduate, undergraduate from a university, it's always to know the background of everything. That's what differentiates between you and a technician, for example, or someone who just learned how to do the technical things. Yeah. Now, what we care about, guys, so I'm going to, as I said, I'm going to skip to prove how these came. And we're going to go right away to the most important proof for us. Okay, so this is the example that we were talking about. Why it's always better, for example, let's say I have a perfect tree here, the height equal 3. What is the internal node? It's 7 here. In this case here, the internal node is only 3. You see, if you have a perfect tree or a complete binary tree, you're going to benefit of storing more data. Okay, so let's get these things also. Now, this is what is very important for us, because that's usually that you actually always need when you're doing the accessing the data. How do you know your tree is very efficient? If you're able to access the height in a fast way. That's why we wanted to always keep our tree either perfect or complete or balanced. Now we want to prove that n equal 2 to the power of h plus 1 minus 1. Why? We can say that at each level, there are what? 2 to the power of L. Correct? So the tree is what? So if I want to calculate the whole number of this, if I know that it's perfect, so what would be? I just need to add these numbers together. So that's why if you add these numbers, so 2 to the power of L plus 2 to the power of L plus 2 to the power of L, you're going to just have 1 plus 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 2h at the end. It's going to give you this. This is also an important thing. Again, you'll find a boring step-by-step details about all of this in the video. Yes, Abed.
This is particularly for
Perfect. That's perfect. Why? Because our idea is what, guys? Our idea we want to reach now, I'm skipping a bit, we want to reach how to prove that using a complete binary tree is still beneficial. Because we said a perfect binary tree is not very practical. We're not going to see perfect binary tree all the time, something perfect. So we're starting that, okay, a perfect binary tree is the easiest way to get this proof. Because if I don't tell you this is a perfect binary tree, can you guess what is the total number? It's very hard because it may be anything, right? You don't know unless you see the tree in front of you. But if I tell you, you have a perfect binary tree of height 3, you're able to calculate it because it's perfect. You know that it's always filled, right? So now we want to take this to say, but I can also prove that even a complete binary tree is still as good as perfect binary tree. That's what I want to reach. Okay, guys? So now, as a consequence, because in a perfect tree we have n equal to the power h plus 1 minus 1, this means in a binary trees, obviously, we're going to always have n less or equal than this. Why? Not perfect. So that means if I prove that in a perfect binary tree, so look at this. In a perfect binary tree, I know for sure that the number is 2h plus 1 minus 1. So what is h here? 3. Correct? Okay. If I don't have these two here, I can't guess exactly what it is, but I know for sure that it may be less than or equal from this number. Okay, just basic things. Okay. So now, if I do the math, I'll end up with what? In a binary tree, if I have n is less or equal than this, I can say I will just bring the 1 here, n plus 1 less or equal than this. How can I get rid of this? Log n. So I'll have log of n plus 1 and log of this will end up with h plus 1. So I know that the h is going to be always greater or equal than log n plus 1 minus 1. That means it's going to be what? I want to talk about O of n here, and I have this. I don't care about the n plus 1 and minus 1, right? I'll say log of n, correct? Okay, so let's see now. Now we just arrived to the complete binary tree. How are we going to prove this for the complete binary tree? We said we know for sure, guys, that at h minus 1, what do we have? It's perfect. So I know that this one here, I can calculate what is n for it, correct? Okay. What is n for this one? Why it's 2 to the power of h minus 1? Not because we said in a perfect binary tree, it's 2h plus 1 minus 1, right? But here, I have 2 to the power of h minus 1. Did I make a mistake putting this here? Who said no? Why it's 2 to the power of h? Exactly, guys. So look, I'm talking about the complete binary tree. We said till here, till this part, that's h. Here, what is h? That's h minus 1. So if I'm using this rule here, I'm going to replace this h by h minus 1. So it's going to be 2 to the power of h minus 1 plus 1 minus 1. It's going to end up of 2 to the power of h minus 1. Good? Okay, very good. Then we know that to the power of h, n is going to be between this and this, because this is a perfect binary tree. Correct? So this is a perfect binary tree. It has to be less than this, but also we know that it's greater than 2 to the power of h, because it's a complete binary tree. And then we're just going to continue with the math here. So how did we get rid of the minus 1? We just switched this less or equal to less. And then we did what? Log n, everything is log. To get rid of the 2, we ended up with h less than log n. And then at this point, h is an integer. So we're going to get the what? what's called, not the ceiling, the floor of the log n. So technically, if I want to say O of what, it's O of log n. That's what I care about. So what I want you to take from this, guys, that I proved, even if it's not a perfect binary tree, it's going to be log of n my height. I proved this. Again, guys, you can watch the video step by step. How did we come up with the math here? But the whole idea here is that I'm able to prove that in a perfect binary tree, the height is going to be log of n. But then I'm saying we're not going to be able to always have a perfect binary tree. So let's see, the closest thing to a perfect binary tree is a complete binary tree. Why? Because h minus 1 will be perfect. Can I still prove that h will still be log of n? I just proved here that yes, it can still be log of n. Now, when you're using this in the midterm and in your life at the programming, you're not going to think about how did we get to the proof, like mathematically, but you will know that if I have a complete binary tree or a binary or a perfect binary tree, I know that h, the height, is going to be log of n. So what does this mean? This means, guys, this means this is my h here, correct? That means the distance between this and this is log of n. So if I want to go from here to here, log of n. So if I'm going to go to here or to here, it's going to be less than log of n. So the maximum that it's going to cost me is log of n. That's what you want to know, that this is not linear anymore. Being able to reach for the full height while staying in log of n. Okay. Will all make more sense when we start implementing them and everything. But now I need just from you to know the logics and everything. And please, please, please watch the video. I made them interactive for a reason. For example, I'm going to ask you a question. Okay, what would this be? The video will be paused by itself. You're going to choose a question. Now, so these are a summary of the rules, but these are the ones that you actually need to know for sure, these two always. So these, we can say that you need, if you're not able to understand, you need to actually memorize these. You need to always know that when I have a complete binary tree, it's always going to be h of log n. And a perfect binary tree, we said, is going to be log n, n plus 1 minus 1. So what does it mean? O of what? Still O of log n. Okay, Abed.
So the height is the same as the time complexity of finding an element.
So here I want you to think about it. So what do we mean by time complexity? Guys, here we have a question. So is the height the same as the time complexity? If I tell you yes and move on, no, I want you to understand why is the same. So what is time complexity?
The time needed.
What are we measuring? Yeah, the time. Exactly. So technically the time that we want to find the worst case of something, right? For example, if I have, let's say, not an array, let's say I have a linked list. Okay. I want to reach, what is the worst case here? For example, the last element, I know the tail. Let's say the element before it or whatever is going to be O of what? Why O of n, the time complexity? What are we measuring here? The worst case. So what do you mean by worst case? The worst case, that means what I'm looking for is here. So I have to traverse everything to reach to it, correct? Okay, so the time complexity, guys, is that what is the worst case for me to, how can I measure my worst case to get something? Now, if I'm not using this linear thing, I'm using a tree, like this one. So what is my worst case? Is here that it has to be one of these. That's my worst case. That's the furthest I can go, right? So that's why if I'm able to figure out what is the distance here, that means it's going to take me maximum this distance. So if my distance is log of n, so it's going to be only log of n. Similar to the linked list, if my number of element, the size is n, so it's going to take me O of n. Did you get the idea? Okay, so what we're measuring here, how can we measure the worst case? The worst case can be, that means I'm asking something here. That's my worst case, because maybe I'm asking something here or here is going to take me 1. But when I say big O, is the worst case. So I'm looking for something here. And if I prove that the distance, the maximum distance can be log of n, that means the worst case is going to be log of n. Okay, if I know 100% that the maximum distance to arrive to my house is 10 kilometers, there is a way that I can get there through 5 kilometers or 2 kilometers or whatever, but there is one that's the worst thing. I can say, okay, my worst case is 10 kilometers. So my worst case is the log of n. Is it clear, guys? So now, if we go back to the ADT, we said we're going to have left child, right child, and sibling, expand external, remove above external. Why did we add these also extend, extend, and remove? So let's see what do we mean by that. If I have this, and I want to keep it a binary tree. So I want to remove this. I removed it. Can I still call this a full binary tree? Full. No. That means whenever I want to delete this, I'll have to delete it like this with its parent. So this will be, so that's what you mean remove above external. I have to actually remove the one above it. That's the only way for me to keep it a full binary tree. Okay, because it will not be a full binary tree. We're going to have a slide for it. You'll be able to understand it. Now, the pre, post, and in order are very, very important. You're going to cover them and on Monday in the tutorial also. And I'm going to, don't worry about it, even if you didn't get it in the tutorial, we're going to actually do it again another time. We said to be able to get to this thing, we need to traverse. So because it's not linear, I have to choose a way to traverse. So there is something called pre-order traversing, post-order, or in order. I made it easy for you. We'll have pre-order called visit, left, right. That means, what do you mean by visit? So I have this, like this. So that means when I'm here and I'm doing visit, left, right, I have to visit. That means I have to execute what is in here. Then I'll go to the left and execute what's here, and then I'll go to the left. I'm done. Do I still have any left here? Do I have any right here? No. So I'll go back and go to the right. Now, in the case of the post order, I'm not going to visit this. I'm going to jump right away to the left, right away to the left, and then so we're going to see it. Now, these are the algorithms, how we are able to describe them, how we are able to write these pre-order. How can we explain it to the machine? How can we do that? If I'm saying pre-order need to be what? Visit, left, right. That in my algorithm, I'm going to say I have to visit first. Now, can I just go right away to the left? What if it's an external node? What if it's a leaf? So I have to check if this is internal or not. If it is internal, then go and do pre-order for the left child, pre-order for the right child. What is this called? What technique is this called? Yes, Anthony.
Transfer search. We go.
No. Don't skip steps. That's the last thing we're going to see.
No bad.
Basic stuff. What is this called in programming? Not in programming. What is this? When you call yourself recursion. Do you see? So you're just basic things, recursion, guys. Okay. So you can write the algorithm. So here again. Now, step back. What we did first? Why did we choose the ADT? Because we had a problem. What was my problem for me to create this tree? Why did I create this tree and I didn't use the linear one? What was the problem?
Get a better time complexity.
Oh, exactly. I wanted to solve to have it faster, more efficient. So that was, for example, my problem. Now I need to write an algorithm to implement this problem. Do you remember we have a problem, algorithm? Okay. So this is one algorithm using recursion. We're going to show you that you can write the same ADT in the same traversal, but in a different way. And these are not the only two ways. Online, you're going to find other ways. Maybe one day you're going to write your own way, okay? For the post-order guides, we're going to, as you can see, visit them and, we're going to go to the left, right, and then visit. Okay, very good. Now the in order is what? Is left, visit, right. So we go left, we then visit, then we go right. Let's take a look here. I have this. If you look at it like a human being, it's going to be obvious A minus B. The machine has three ways to look at it. It's going to be either A minus B, AB minus, minus AB. So the in order will be what? The in order is left, visit, right. So I'm here. I'm not going to execute. I'm going to go to the left. So that's my first left. Then I'll go back and visit. So that's why I have minus here. Then I'll go to the right. But if I'm using a post order, it's what post order?
Left, visit.
No, left, right, visit. And this one, the pre-order is visit, left, right. You're going to get used to it. So again here, if I'm going to left, so I'm going here first, that's A. Then I'm not going to minus, I'm going to also right, L, R, and then. Good, okay, so let's do this together, guys. Who wants to do the in order for this? Because here, if you think about it, we said in order, it made sense, A minus B. So of course, I should use the in order all the time for arithmetic. Fida.
So in order left, visit, right. So we will.
So left, visit, right. Okay, now I want you to follow this method. Each time, because it's going to get more complicated than this. You're going to say, I'm here, left, visit, right. So I need to start with left. So I'm going to go here. I want you to also write another left, visit, right here. Okay? Now, what are you going to do with that? Another left.
The left, so we will.
So again, left, visit, right. So you're going to try to go to the left. Is there any left here? Okay, so I'm going to go to visit. I'm going to visit this, that's 2. Where should I go now? Step by step, not like the answer.
Now we visit, so right.
Exact. So I finished from left, I finished from visit, I have to check for the right. Do I have anything on the right? Okay, so I need to go step back. This is done. What do I do now? Visit. So I'm going to take the X.
Now we have to check right.
Now we have to check right. So I go here.
Left, visit, right.
Left, visit, right. So where do I check? Left. I'm here. Left, visit, right. I don't have any left. So visit. So that's going to be A. Right. I don't have anything.
So we step back step.
That visit.
Now visit, so we add minus.
Minus, and then?
Check if there is right.
Okay.
Now there is right.
Nothing, nothing, and then 1.
Also.
Okay, let's, thank you so much for that. Let's go with someone else. Now, so I'm done from left, visit right. So where should how should I track my, yes.
I have to go all the way back up to the root.
Exactly. Why up to the root? Because this is done, and this is done. I need to do now the visit. Complete, correct. So what? It's going to be what? Plus. Then this is done. I need to go to the completed. Continue.
Right, then another left, visit right, and then we go left.
So here.
Visit right, there's nothing, so we're gonna go visit. Go 3. Go back up, times, and then B.
Then B. Good. Okay, now, if you look at this, I have 2 times A minus 1 plus 3 times B. Because it worked here, we thought it's going to work. Would this be correct? In this case here, as a human, I'm looking at this, it's not correct for me. It's 2 times A minus 1. But here, if I do it, if I feed it to the machine like this, it's going to be 2A minus 1. So this shows me that no, in order, for example, if I'm following the same algorithm that I showed you, it's not going to work. In this case, Taha, as a computer scientist who took this course with me and got a job, and you're facing this. Someone in the company found this problem. And he's freaking out, oh, this algorithm is not working. So what are you going to suggest to him? What can we do if the algorithm is not working? So technically, if the algorithm is not working, we should maybe modify.
The order is not working, we find the errors.
For example, very good. So the first step, you can say, you know what, we have two algorithms. We have the in order. Let's try the post order and see if it's going to work. Now, let's say the post order also didn't work. So you know what? We are computer scientists. We can just modify the algorithm because we didn't implement it yet. It didn't take lots of time from us to do the Java or the C++ thing. It's still an algorithm on the paper. So I can just modify this algorithm, make it a bit better because it makes sense. It's almost good. So what if I just make it better? So instead of having this, guys, this in order, maybe I can add something here, like an if condition or something that will make it better. Okay, so that's the steps that I want you to think about it when you're designing or you're solving a problem. Don't freak out like Taha's colleague. Okay, guys, so who's going to do the post order with me? I want someone now who got confused about the in order. They are not very sure about it, so they want to try the post order with me. Taha. Let's start. So what is the post order?
We have.
Sorry. Okay. So the first we got this. Okay. So the post order is what?
We have left, right, visit.
Exactly. So we're going to start with the left, right, visit.
First, we go to the left side.
I go to the left.
So we have left, right, again. So we go to the left again. We have two. So here, we also have left, right, visit, but there's no left.
It's a leaf. Exactly. We're going to go with the two. Then after that.
You go back to the parent.
So this is done. So I'm here again.
Now I have to go right.
Exactly. Why did I go right? Again, it's a recommendation from me. Always leave them above the nodes. It will be easier for you in the midterms. So right, I have to go here. So left, right, visit.
Visit, so we do it left.
So we went here, and that's in A. So let's take someone out. Who wants to continue? Yes.
From here, you go back up to the minus and then right. It's a leaf, so you visit it. We have a 1. Then you go back up to the minus and visit it.
Okay, perfect. So that's minus. Thank you. Who else want to continue this? If it's not very clear, please. Try. Yes? So now where I finished from here, right? I will go back here. Exactly, because this is done. I can visit this, so I can have times here.
Go back to the front.
I go back here. This is done. So what should I do?
That's right.
And then
Left, right, visit.
left. So that's 3. Left, right, visit. So that's 3. And then who wants to continue? Luke.
I'll go right.
You go right to B, which is B, and then, okay, this also didn't solve it. So maybe we need to actually modify the algorithm a bit. So we're going to, yes, there is a plus. So we're going to modify it. This is one way to modify this algorithm. I'm going to create this variable here to call it operator stored at V. So I'll just change it and I say, you know what, we have X, we have Y. So the X will be the left child, the Y will be this, and then I'll have a variable for the operator. Let's see if this is going to work. And then I'm going to return X operator Y. So I just changed the whole algorithm for it to work, and it's going to work. If you see this, I'm going to skip it now so we can do the woo clap, but we're going to continue. I wasn't able to finish everything today, but please watch the lectures. So on Tuesday, we don't spend too much time, okay? So here you can try it at home by yourself. I'm not going to publish the notes today because I want you to do this on your own. I'll publish the notes maybe tomorrow, for example. okay, or on Monday. So let's do the who clap now, guys.
First one we did.
Before we do the woo clap, who can think about something, a different way of not using a recursion? What can we do to solve this arithmetic problem without using a recursion? We use a different type of something.
Let's say the original one where we had it in order, but we were missing parentheses. For example, 5 minus 1, can we add a child cost of each element, so it's a 5 element?
Yes, exactly. So this is sometimes you'll find in one of the labs or one of the exercises is this. They will give you this original algorithm. We're going to, okay, modify this algorithm to solve this problem. We just gave an example of having this operator. Another way actually is you're going to say, whenever I see this, add a opening parenthesis. Whenever you see this, add a closing parenthesis. So this is another way to solve it. Exactly. So this, we don't only have one algorithm. We can have many algorithms. But what you want to pay attention to is you don't want to create an algorithm that will solve the problem, but will make it linear again instead of keeping it log of n. You know what I mean? Like having like an extra loop for no reason just to solve the problem, and then you ruin everything. Who had, yes?
You have a while loop and then end it when you get back.
We don't want to go to with a while loop because of this, because you're going to end up with what? With O of n. Another way, guys, if you remember, we said, how did we solve arithmetic stuff with the stack? Stack is very useful for arithmetic. Why? Because you don't have to loop. It's going to always be on the top with the stack. So here, there is an example. If you continue with the slides, you're going to see how we implement the same exact thing with the stack, for example. And then we're going to go with the implementation of how can we implement this with arrays and with things. There is a chance that on Monday, instead of the tutorial, I'll just complete this myself, okay? So I'll complete this, and then this will be instead of the tutorial. Because I don't think you're going to be able to benefit from the tutorial on Monday if I'm going to continue explaining on Tuesday. So I wasn't able to finish this, unfortunately. It's okay. So I'll send you an email about it. Let's start. What is this tree? Very quickly. We only have 7 minutes to finish this. What is this tree? Is this a maple tree, general tree, binary tree, full binary tree? Someone who loves Canada too much. Of course, the general tree. How would this be a binary tree, guys? How would this be? Because we have 3 children, right? Binary mean 2. Okay, so what is this tree? Is it a binary tree, full binary tree, complete binary tree, general tree? So usually always choose the best answer, even though, like, for example, this can be a binary tree and something else. So what is this? Everyone? So we have a binary tree, 65%, full binary tree, complete binary tree, general tree. Of course, not general tree, but let's discuss if it's a full binary tree. Who can tell me why it's not full binary tree? Someone who didn't participate today. Yes. Exactly. So what is the definition of a full binary tree, guys? It means it has to be, it's either a leaf or 2 children. We'd only have one child here, yes.
Is the best answer the most specific answer or the most general answer?
Most, like for example, if you have a full binary tree and a complete binary tree, you're going to choose complete binary tree. So it's the one that have the other ones inside it. So in this case here, it's not a full binary tree, but is it the complete binary tree? It's not. Why it's not? Is it left filled? No. Is the h-1 perfect?
No.
No. So that means, of course, it's a binary tree. Correct? Okay, what about this tree, guys? Is it just a binary tree, full binary tree, complete binary tree, perfect binary tree, or BNC and BND? You chose the wrong one. So this is just giving us a summary, just to make everything stick in our head, without talking to these guys. Guys, we only have 5 minutes left, so let's please finish this quickly. So what do we see here? We see full binary tree, complete binary tree, and then BNC. So the majority are 50% BNC. Why it's full binary tree? Because every node has either a leaf or has 2 children, right? But also, why it's a complete binary tree? H-1 is perfect, so this one here is perfect, and also it's left filled. Okay, so they are B and C. The answer. What is this tree? What is this tree, guys? Quickly.
Same thing. Perfect. I will stay here. So once we ask these, I think so. I think so. Now that I actually following. Perfect. Obviously.
Guys, complete binary tree, of course. Why is just a binary tree? Why is just a binary tree, guys? Yes. Guys, we're almost done. Yes.
-1 is complete.
So H-1 is perfect, and then it's left filled. So it should be complete binary tree. For the people who answered just the binary tree, why?
I assume that complete binary tree implied that it was a full binary tree.
So that's what I meant. So usually, you're going to choose the one that covers everything, right? Yes.
So it's left field, just one.
Yes. That's why I'm giving you all of these different examples. Okay. If I give you this, you're going to choose complete binary tree, because a binary tree, it's not always complete binary tree, but a complete binary tree is always a binary tree. Okay, so let's go with this question. The height of a full binary tree of n nodes is floor log n. Is this correct or not? Is the height log n? Is it log n? True, false, true, false. It is, of course. Full binary tree, that's true. Yeah, we didn't say it's full binary tree, not, yeah, even me, I tricked myself. So only perfect binary trees and complete binary trees are log of n. Okay. The height of a complete binary tree, yes, so that's the true one. Complete binary tree. And by the way, sorry. The height of a complete binary tree is log of n. The height of a perfect binary tree is not log of n, but it is O of log of n, because the height is log of n-1 plus something. So the height, it's not log of n. Okay? You'll check the slides and you will know it. In a complete binary tree, what is the total number of nodes? Very quickly, total number of nodes, complete binary tree. We said a perfect binary tree is n equal 2 to the power of h plus 1 minus 1. So this is the right answer for a perfect binary tree. A complete binary tree may be what? Equal or less. So that means it's going to be this one, because a complete binary tree is not always perfect. Okay, we'll continue these later.
Oh no.
Have a good day, guys.
That takes you 5 minutes. Give me 1 second. Give me 1 second to finish this.